Welcome to New York City Atheists, live on tape, brought to you by New York City Atheists Incorporated. I'm your host, Dennis Horvitz, the David Letterman of the Hopelessly Damned. Today we're going to try to answer a few questions, or at least explore them. Is there life elsewhere in our universe? Sure, if you get there on a Saturday night. But, look, I do this for free, okay? I'm doing this from one of our notorious Sunday brunches, New York City Atheist Sunday brunches. In any case, we're going to try to explore today questions such as how do we define life? What conditions are required for it? Where in our galaxy could life other than on Earth be? Are there other intelligent beings? Are they on their way? We should probably cue the spooky space music right now, but we don't want to pay the royalties. Anyway, in any case, to answer this question and related questions, our blank speaker today is Dr. Fred Walter. He is from Berkeley, California, and he's now a professor of astronomy at the Department of Physics and in astronomy at Stony Brook. And in addition to some of the aspects of astronomy and biology, some of the topics perhaps that we will touch upon today is, first of all, the physical conditions of the universe as it exists now, and the age of the Earth. I'm sure that we'll probably get into the young and old Earth creationism and during our question and answer period. And the Drake equation, which is, I guess, the best means so far by which scientists have to estimate the possibility of extraterrestrial life, and I guess that would be intelligent, also including intelligent life elsewhere in the universe. And the information theory. How would we recognize signals from intelligent life on other planets? Well, if they call collect, that would be one way. But, in any case, I'm not the one that's going to be answering this question, so it gives me great pleasure to introduce Dr. Fred Walter.
So, to do astrobiology, you have to ask the right question. A lot of science is asking the right question. It's not, getting the answer is not all that important. We don't know what the right answer is. You want to get an answer, but it's the question that's important. So, what are we looking for? That's the question in astrobiology, and how will we know when we found it? Okay, we know what life, as we know it, is like. It lives on water, requires liquid water and all that, but there is also the possibility for life as we don't know it. We know what environments work on the Earth, any environment that supports liquid water. What environments could life as we don't know it entail? Again, we don't know. Science fiction writers are probably not ingenious enough to come up with all the locales. Maybe some of you are, but it's a question. Where is life? And will we know it when we find it? So now we get away from biology and the chemistry part of the talk into the astronomy part. Solar system. What are the locales in the solar system where life might exist, other than the Earth, of course, where life does exist? And what constitutes evidence? How will we know it when we find it? Well, evidence of life could consist of a large multicellular object walking in front of your camera. That would be too easy. Probably not going to happen. So, evidence will probably consist of, well, that's the images of bodies there, but we're most likely to see cells or fossils. Okay? Most living things on this planet are, most species are dead, most things are fossilized. That's probably true elsewhere as well. So we have to find fossils or cells. Those are hard to see. You need microscopes, you need to dig. They don't just walk across the field of view. So it's going to be hard to find it. Artifacts. Maybe there are artifacts out there that we can recognize. The pyramid, something like the Great Pyramids of Egypt on another planet, that might be good evidence for life out there. Maybe a real flying saucer, if anybody actually got evidence. UFO people like to say that they're being visited, but they've never produced any evidence of it. So if you could actually have an artifact, that would be very strong evidence that there's something out there. Another one is non-equilibrium conditions. Life is a non-equilibrium process because anything that violates the second law of thermodynamics locally is non-equilibrium. You are going against the laws of thermodynamics. You're turning a disordered state into an ordered state. These three spectra on the right, these are plots of basically intensity versus wavelength for the atmospheres of three planets. So this is Mars, this is the Earth, this is Venus. And this is if you take a telescope, put a grating or a prism in front of the spectrograph, disperse the light into its colors. This is the infrared. You don't need to know what the wavelength is. The brightness is up here, and here's an absorption line due to carbon dioxide. There's carbon dioxide in the atmosphere of Venus, the Earth, and Mars. If you look at the atmosphere of the Earth, which actually means you're looking at the atmosphere, you're looking at the moon, the Earth light is reflected off the moon. What you see that you don't see on Mars and Venus is you see water in the Earth. Well, that's okay. Earth is just the right temperature. Venus is dry and Mars is pretty dry too. Earth is humid. It's got water. That's not a non-equilibrium thing. Water is actually quite abundant in the universe. What you see in the Earth is ozone. Ozone is a non-equilibrium product. Ozone is created by, of course, ultraviolet reactions of breaking down other more complex molecules, but it implies that there must be some non-equilibrium chemistry going on in the Earth's atmosphere or on the Earth's surface, generating these gases that break down into ozone. So if you were an alien astronomer taking a look at the planets in our solar system and you look at these spectra, you'd say there was something interesting about the Earth. There's some non-equilibrium chemistry. We'll see some evidence of non-equilibrium chemistry, possibly on Mars, in a little bit. So that's evidence there might be something interesting going on the Earth. And we know on the Earth that's due to life, which is a non-equilibrium process. The other thing is waste products. Waste products are evidence of life. You don't have to see the living thing, but you can see what it left behind. And we, of course, leave a lot of stuff behind on this planet. You can see this in the atmosphere and on the surface. When we look in the solar system, if we're guided by life as we know it, and we're looking for things we understand, we have to understand the concept of the habitable zone. The habitable zone is places in the solar system where you can have liquid water. We need water for life as we know it. So where is liquid water? Liquid water exists where the temperature is between 0 and 100 degrees Celsius at a given pressure. You need some pressure, you need an atmosphere. If in a vacuum, you don't have liquid water, it sublimate. So for liquid water, you need an atmosphere, but you also need to be a certain distance from the sun. This is the mass of a star, one is the sun, so they come over here. Here's our solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Pluto, which is not a planet anymore, but it's still up there. Here's the Earth, and this yellow band is the habitable zone. If you look at the sun, if you move the sun basically from this distance, or the Earth from this distance to this distance from the sun, anywhere in there, water can be liquid on the surface. In here, it's going to be hotter. Out here, it's going to be colder. But anywhere in here, water can be liquid. That's called the habitable zone. Okay. So in our solar system, where do we find liquid water? In a narrow band, a certain distance from the sun, which marginally excludes Venus, and it marginally excludes Mars. Now actually, the habitable zone is somewhat larger because the habitable zone also depends on the atmosphere of the planet. You've heard of the greenhouse effect. The Earth's atmosphere keeps the planet about 30 degrees warmer than it would otherwise be. It would be pretty cold if you didn't have carbon dioxide and other greenhouse gases, including water vapor, in the atmosphere. You put enough greenhouse gases in a planet out here, you can have liquid water. You have fewer, you can have liquid water in here. So there are 3 planets in our solar system that are in or close enough to the habitable zone to bear close scrutiny: Mars, Venus, as well as the Earth. If you want to look at other stars, that's what the
vertical extent is these are cool stars, they're less massive and cooler than the sun. The habitable zone moves in closer, and it moves further away as you go to hotter and brighter stars. And that's just a consequence of the fact that the equilibrium temperature of a planet depends on how far away you are from the star. A brighter star at the same distance gives you a hotter planet. So this is the habitable zone. If we are going to require liquid water, we can find liquid water. We can find a habitable zone around any star. If there's a planet at the right distance with an appropriate atmosphere, it could have liquid water, and hence it could have life as we know it. And life as we don't know it could be anywhere. There are no constraints on it. So liquid water needs temperatures of 0 to 100 centigrade. It needs pressure. It needs an atmosphere. Well, it doesn't need an atmosphere. It just needs a source of pressure. We'll get to that about Europa. And remember that the temperatures are controlled by atmospheres and not by the irradiation alone. I'm not going to talk about Venus because, well, Venus is not a very good place to look for life because it's had a runaway greenhouse effect. It's very arid. And also, I don't have time. We'll talk about Mars. Mars is out at 1.5 AU. That's an AU in astronomical units. This is from the Earth to the Sun. So Mars is 50% further away. It gets less than half the solar irradiation that the Earth gets. It's on the edge of the habitable zone. In principle, if it had a big enough atmosphere, which it doesn't, you could have liquid water on the surface. You cannot have liquid water because the atmosphere has a pressure of about 1 bar. 1 millibar, 1,000th of the Earth's atmospheric pressure. The atmosphere is mostly carbon dioxide, but there is water vapor in the atmosphere. Not much, but there is some. But water is a very common constituent of the universe as we know it. Oxygen is very abundant, hydrogen is the most abundant element, and water is, hydrogen plus oxygen, is very common. Mars is interesting from a geological point of view because it has rift valleys. That means it had plate tectonics. That means it has the largest volcanoes in the solar system. You can see them here. This, and this are very large volcanoes. They're about 300 kilometers, 400 kilometers across at the base. If you were to put one in Connecticut, it would stretch from Boston to New York City. Those are big volcanoes. So this, at least once, was a very interesting place. This is what NASA's goal, one of NASA's goals, and the planetary program's goal is to find, well, you can tell me what that is. You can see that, right? We want to find water on Mars. So, is there evidence for water on Mars? The answer is yes. Here is a picture from one of the Mars rovers. You see clouds. Those are cirrus clouds. There's water vapor. It's ice. But there are ice crystals in the atmosphere. Look at the surface from above, dendritic channels. You ever fly over the American Southwest and look out the window of the airplane, you look down, that's what you see. You see dry river valleys. That's exactly what that looks like. There's some minor arguments in the geological community about whether these are lava flows or water flows, but it's about 99% for water now. We see some on the moon which are actually lava channels, but these are dry riverbeds. There was running water on the moon when, a long time ago, over 3 billion years probably, there isn't much erosion on the moon. But those are dendritic channels, there was running water at one point on Mars. You see frost in the morning. When you wake up on Mars and look out of your window, or go open the tent flaps, you'll see frost on the ground. It gets very cold in Mars, and now that will not turn into liquid running water. That will sublimate as it heats up. But this is a photograph from orbit, and the whitish thing is frost that's collected at the bottom of the crater. And this is from the Viking lander of 1976. It's a frosty morning in Utopia, Planitia. The Phoenix lander landed about a year or so ago, I forget, May 28th, just over a year ago. And it happened to land. They're out there looking for evidence of water. It happened to land right on a patch of ice. How lucky can you get? That's that white thing. This they think is ice. Now, it's not 100% certain, but it sure looks like ice. The robot arm they had on it to sample things couldn't stretch far enough to actually get to it, but that certainly looks like ice. There's evidence again, of lots of water in the past. This is a photograph from one of the Mars rovers. This place is a wall of a crater. And if you look at this, this is not in the best focus, but if you look at the original picture, you can see very fine striations along here. This is sedimentary rock. It's laid down in layers. It's laid down by sediment precipitating out of water, out of standing water. There was a lake bed here. There was a lake here. It's also got salt residues in it. Salt was dissolved in the water. It precipitates out when the water evaporates. And it's been sampled by the rovers. So there's plenty of evidence that there was running water on Mars. Now, the water was probably highly saline. Of course, that's not an issue for life on Earth. Maybe it's not an issue for life on Mars. Is there life on Mars today? The Martian rovers have seen no evidence for things moving around. They've seen no footprints. They've seen no fossils sticking out of the ground. So the answer is there's no large-scale life, but they're not looking for single-cellular life. We don't know if there are bacteria around. But there's one very interesting bit of evidence. This can be interpreted in many ways, well, at least two ways. One is pro-life and one is not, I suppose you could say. There is a non-equilibrium gas in the atmosphere of Mars. It's called methane. Here's a spectrum taken by the European Mars Express mission. And this is, again, brightness versus wavelength. And these dips are all due to various gases absorbing in the atmosphere. This little dip here is due to methane. Well, methane is very interesting because methane is non-equilibrium. Methane is destroyed. At the distance of Mars, it will be in the Martian atmosphere. Methane will be destroyed on a timescale of about 300 years by solar ultraviolet radiation. So any methane in the Martian atmosphere must have been put there fairly recently, within the past few hundred years. Where does methane come from? On Earth, methane comes from cows and termites, mostly. Some of it comes from natural gas. Well, it is natural gas. So when you dig a well and release some natural gas, the methane goes to the atmosphere. And that's another biological process. So methane in the Earth is mostly from biological processes. It's curious that the places on Mars that have the most methane seem to be the places that are co-spatial with water vapor in the atmosphere or in the ground. There's evidence about subsurface ice. So it may well be that if you're very positive here, it could be that we're seeing evidence of Martian methanogens, bacteria that live on methane and water, and they produce methanogens can both produce methane and live off of it. I'm not a biologist. I don't need to know these things. Anyways, it's possible that we have Martian bacteria here. This could be evidence of Martian bacteria. On the other hand, this could be evidence of non-biological processes called clathrates, which are merely ices with gas dissolved in them, which are evaporating for whatever reason. Of course, then that begs the question of where did the CH4, the methane, come from in the first place? It could have been biological, could have been left over from very early in the solar system. There's a lot of methane ice in the outer parts of the solar system that is non-biological in origin. So this is not clear-cut evidence, one way or the other, but it's enough to tweak our interest, to say that maybe there is something interesting about Mars, maybe there is something living on Mars. The conditions are as extreme as they are in Antarctica, although Antarctica has more of an atmosphere. Things from Earth, the right ones, could live on Mars. Life cannot be ruled out on the basis of what we know about Mars. So maybe there is something alive on Mars. There are people who will tell you that there are artifacts of intelligent life on Mars. This photo has been very heavily processed. This is what that was a photo from '76. This is what you see when you look with a better camera. It's an eroded mesa. There are other things on Mars. There are things on the Moon too that you can interpret in many ways. Be careful when you look at planets, planetary surfaces, and interpret these artifacts, because the human brain is hardwired for residue. Further out
Well beyond the habitable zone now, we have Jupiter. Jupiter is not the place to look for life. Jupiter is a failed star. It's basically made of gas. Europa is the second of the Galilean satellites from the inside out. It's bigger than our moon. When you take a photograph of it up close, well, that's part of it. It's got a very smooth surface. It's got the smoothest surface in the solar system. And when you look at it really up close, that's what it looks like. Those of you who may have grown up in the Northeast or the North and used to go skating outside in the winter before global warming melted everything, you might recognize this. This looks like the surface of a lake. In February, it's ice flows, and we all know that the surface contracts and expands, and you get cracks in it. And that's exactly what this looks like. We believe that the surface of Europa is ice, liquid ice, solid water, solid ice, okay, H2O. There are some impurities on the surface, but it's mostly water ice. That's what it looks like. We don't have a better explanation for it. If there's water ice, maybe there's liquid water. In fact, there are two models for Europa. The first model says that we have a cold, brittle surface ice, and the thickness of the ice here is tens of miles. It's not a small moon. And then underneath you've got this warm convecting ice. What does warm mean? Warm means it's more than 32 degrees Fahrenheit, 0 centigrade. It's basically held as ice by pressure. Or it could be exactly at the freezing. Where does the temperature, well, let me do the second model, says that you get the same surface, which is your solid ice covering, and then underneath you've got an ocean. How deep is this ocean? Well, this goes from a few tens of kilometers down to maybe a few hundreds of kilometers down. There is probably more liquid water on Europa than there is on Earth. In fact, even if you go to the ice scenario, there's more water on Europa than there is on Earth. Why? Well, Europa is far enough out. The water is a volatile molecule. It evaporates at the temperatures you get at the Earth. It sublimates unless you've got atmosphere to keep it in. So you don't have much water in the inner solar system. You go to the outer solar system, the ice line is about where Jupiter is. Further out than that, there is a lot of water. There may be more water on Europa than there is on the Earth. And it may well be liquid. Well, how do we keep it liquid? This is far away from the habitable zone. The temperature is very, very cold. The reason is tides. The reason is that Europa is orbiting Jupiter, which is 1,000 times the mass of the Earth. There are very strong tidal forces acting, and the tides heat up the interior. The tides are so strong that Io, the innermost of the Galilean satellites, is basically molten. Io is what the biblical hell is like. It's basically molten sulfur. Okay, sulfur and brimstone and all that stuff. You go out to Europa, it's not quite as hot, but there's certainly enough energy from tides to keep the water liquid. Now this points out two things. One, we don't need to be near a star. We don't need sunlight to give you energy. Here's another source of energy, tides, tidal dissipation. So Jupiter can keep Europa warm enough that you can have liquid water in the interior. So it's about freezing. There's enough energy there for biochemistry to occur if you have the right elements. Well, you've got all the elements that you have on the Earth. You've got carbon, you've got oxygen, you've got nitrogen, you've got phosphorus, you've got hydrogen, you name it, it's there. The question is, can biochemistry get going? There's a source of energy, there's a source of basic chemistry. It's colder than the Earth, things will happen more slowly, but it could be that we have biochemistry happening, we can have a biochemical type of life evolving in a place like Europa, 5 astronomical units out of the sun. So here's another interesting place to look. It shows that we don't need to have the surface of a terrestrial planet. We can have something else as long as there's a source of energy. And energy is important for life because life, again, must create disorder out of disorder. Titan is another interesting place to look for living things. Titan is the largest moon in the solar system. It's the satellite of Saturn. It's 10 astronomical units out. It's even colder than Jupiter. Its temperature is minus 178 Celsius on average. The atmospheric pressure is 60% higher than the Earth's atmospheric pressure. It's got an atmosphere that's made of nitrogen with methane and ethane. You want to solve the Earth's energy crisis, you go to Titan and just bring back some of the atmosphere. Lots of natural gas out there. We landed a probe there, the Huygens probe, a few years ago, and here's a photograph we took on the way down. And I look at that and say, gee, that looks like a shoreline. I'm not the only one who said that, I'm not the first, but it looks like a shoreline and riverbeds. It actually looks like part of New England, as far as I'm concerned. The riverbeds look like the dendritic channels on Mars. What could exist here? Not water. Water is a solid at this temperature. Water is as hard as granite. But it could be ethane and methane. It could be liquid methane. Okay? And in fact, we think that we know this precipitation in the atmosphere. The atmosphere has clouds, photochemical smog, which is what happens when UV radiation interacts with hydrocarbons. So we probably have liquid methane and methane precipitating out and forming at least temporary seas and lakes and rivers. So that's another place we can look for life, again, based on hydrogen, carbon biochemistry. At these temperatures, biochemistry happens very slowly, but the building blocks are all there.